Hello and welcome to my talk. My name is Sascha Gaudlitz and I'm a PhD student of Markus Reis at Humboldt University Berlin. And I want to talk about statistical inference on the reaction term in semilinear SPDEs. I will start by introducing a novel asymptotic regime for these kind of problems. So we will consider these kind of semilinear SPDEs. We assume that they are driven by space-time wide noise. For notational simplicity, we assume that the initial condition is plate 0. Then we have here a non-linearity, that is the aim of our statistical estimation process. We want to know what is F in the end. And the leading order operator I will call A. Think, for example, about the Laplacian. And I will introduce a new scaling parameter nu in front of the operator A. That is a real number and corresponds to the level of diffusivity of the system. And here I have simulated the same semilinear SPDE with different levels of diffusivity. So on the left, you see a high level of diffusivity, and on the right, you can see a lower level of diffusivity. And you can see that on the left, there's really everything is blurred out, and you cannot really see a lot of interesting structure or anything really. And on the right-hand side, in contrast, you can see more structure and more, from modeling point, interesting behaviors happening. And this motivated also for us to look at the vanishing diffusivity regime, where we replace the normal operator A by rescaled version and then send the diffusivity of the system to 0. And that also might help practitioners to give them a second handle on improving the estimation process. For example, if they have access to the diffusivity of the system and can actively influence it. Note that from a mathematical point of view, we are doing a time, we are rescaling the time in the semi-group that is generated by A. So actually the parameter nu goes into the time argument here. And if you send nu to 0, then the semi-group will tend to the identity. Okay, so where do we get the estimator from? There's a well-known result. You can find it in many books. It is a Gaussian theorem for semilinear SPDEs, and it basically tells you that if you have a process that, well, you have the law of the process that came from the semilinear SPDE, then this law will be absolutely continuous with respect to the law that was generated just by the linear one without the nonlinearity. And as these two laws are equivalent with this density here, this is really good news from a statistical point of view, because that means we can do maximum likelihood estimation. This is exactly the road that we will follow in this talk. So we first of all make a slight simplification. So we will assume that the nonlinearity is parameterized by a real number, a theta, and that actually goes multiplicatively in front of the nonlinearity. And then you can explicitly write down the MLE, and you know that it satisfies a very certain structure, and the structure that we will leverage on in the proof for a central limit theorem for this estimator. So you see that the estimator is actually the truth plus a deviation, and this deviation is what we need to control later on. So I will call the upper part here M because it is a martingale, and the lower part here I will call I because it is the empirical Fisher information of the system. And then we decompose the difference between truth and estimator into 3 fractions. The first one here, it is the martingale divided by the square root of the expectation of its quadratic variation, and by standard martingale arguments, this will converge to a standard normal. So this term is fine. With this term, it's the expectation of I square root of it divided by the square root of I. So we hope we will prove that this converges to a constant. And then the latter part corresponds to the rate of convergence for our estimator. So we have 2 big challenges now in order to prove the central limit theorem. The first one is we need lower and upper bounds for the empirical Fisher information. And upper bounds are quite standard from SPDE theory, but we also need lower bounds. And these are not so standard. And the second one is we need upper bounds for the variance of this empirical Fisher information. So that is really not standard at all, because we have a highly non-linear functional f here, and also the f, of course, placed into the x as well, because it followed this dynamics. So it's not quite clear how to proceed. Okay, so the two main tools that we used are the following. So first, for the lower bounds on the empirical Fisher information, we use the D'Abrato-Debuche trick. So we decompose the solution into a linear part, okay, this one here, and on the other hand, into the nonlinear part, this one. And then for small times, so for small times here, we can show that the nonlinear part is dominated by the linear part. And as a linear part just corresponds to a Gaussian process, we can more or less explicitly compute how this behaves when we send mu to 0. I will explain the phi on the next slide. Yeah, and for the bound on the variance here, we use something that's called Poincare inequality from Malevin calculus. And this allows to control the variance of a functional of a white noise process in terms of the norm of its Malevin derivative. So the d here is a Malevin derivative, and that is a Malevin derivative of h. And these are the tools that we will use, and the kind of assumptions that we need to make out of this work are the following. So first of all, we need that the Hilbert space that we will solve the SPDE and actually in a 2 space in a suitable nice domain. And then the phi that actually appeared also on the last slide and will appear also in the next slide as kind of the rate of convergence. This is the growth rate of the Hilbert-Schmidt norm integrated over time of the semigroup generated by nu times a. Okay, so this is what we call phi. And then we need two kind of assumptions on the nonlinearity. So first of all, we're having a two-sided bound here in terms of norms to really have the control on the lower bounds for the Fisher information. And in order to make the Malevin calculus work, we use so-called Nemitsky nonlinearity. So the f actually is a composition of a C1 function, small f, with the argument of f. Okay, and the last two are more meta assumptions, and you can find lots of excellent readings on when these assumptions are satisfied. So the first one is we have that solution X to the SPD is actually a random field solution. And then the second one is that we have a formula for the Malevin derivative. And that's actually, if you look at it closely, it's deterministic PDE with random coefficients here. Yeah. So these are the assumptions. And with these assumptions, we can prove the following central limit theorem. So the deviation of the estimated to the truth rescaled by the empirical Fisher information as square root of it goes to a standard normal. And now with these assumptions, we can also quantify how this behaves. And we know it will concentrate around its mean, and the mean goes like phi to the nu. So all in all, we will have a rate of convergence of square root of phi for a central limit theorem. And but the point is that this I is only data driven, we have access to it. And this allows us to construct asymptotic confidence intervals that are purely data driven. So these are, that is the main result so far. It has not yet appeared in a paper that's still under construction. But yeah, I want to stop here now. Thank you very much for your attention, and I'm looking forward to the discussion.